Okay. Good morning, friends, and welcome back to this extra class on heat transfer. Today we are going to continue. We are going to continue on our discussion on heat exchangers. Sadha Sivam, do you have a question? You raised your hand.
No, sir, unknowingly.
Unknowingly, that's okay, fine. So remember in the last class what we said was we came up with this method which is called the LMTD method, or the log mean temperature difference method. Okay. And while we could derive exact expressions for both parallel flow and counter flow, for other configurations like cross flow, shell and tube, etc., it becomes a bit difficult, right? But however, our predecessors have done that job for us. They have given us charts or plots from where we can read out the values of what is called a correction factor F. And the mean temperature difference is therefore that correction factor F times the mean temperature difference for a counter flow heat exchanger with the same set of inlet and outlet temperatures. Clear? And we saw some of the charts. They are dependent on two parameters. One is R, one is P. We defined what those are and so on. So today, let me start sharing my screen. We will start the class by solving two problems. Okay. Meanwhile, I have uploaded the problem sheet on MS Teams. So you should be able to start solving those problems. Okay. But let us solve one of the problems today over here. The problem states that a parallel flow heat exchanger is to be designed to cool 5 kg per second of air from 500 degrees C to 350 degrees C. So these are really high temperature heat exchangers. By an equal flow rate, excuse me, of air again coming in at 90 degrees C. Okay. Let me give you some data. So H of the hot side is equal to 60 watt per meter squared Kelvin. H in the cold side is 30 watts per meter squared Kelvin. Okay. And the Cp of air is 1020 joules per kg Kelvin. Okay. And what we have to do is we have to find the size or the area of the heat exchanger. Okay, so this is what we have to find out. Okay, so what are we saying? We are saying that it's a parallel flow heat exchanger. Okay, so I have hot air coming in and exiting. I also have cold air coming in and exiting. The hot air temperature 500 degrees C at inlet and 350 degrees C at exit. Cold air 90 degrees C at inlet, exit we don't know. Okay, so please look at this problem and try to solve it. Okay, let's take, it's 10:23 by my watch. Let's take 5 minutes and then I'll ask you. Okay, anyone has the answer? If not the answer, at least how you would do it? Simple problems that you can get. Very, very standard, straightforward problem. Okay, 5 minutes done. Of course, someone please tell me how you would solve it. Even if you don't have the final answer, how would you solve it? Don't somebody should be able to answer.
So can we first calculate the delta Tm, and then can we write delta Tm by R is equals to m dot at Cph Thi minus Dhe, and then from that we can write R as 1 by Ha and then calculate A.
R. Okay, that is you're talking about, right? Yeah, I think
Yes,
that's
but
yeah, correct. So let's do this. So I need to find A, and for A, what is the expression that we know? Q is equal to U, which is the overall heat transfer coefficient, A delta Tm. Okay. So this is my equation that I know from where I can find A, provided I know everything else. So do I know everything else? So one, do I know Q? Yes, I do, because it is m dot H Cph Thi minus Dhe. Yes. Do I know all of them? You bet I do, because m dot H 5 kg per second given, Cph 1020 joules per kg Kelvin, Thi and Dhe 500 and 350. So therefore, I can find the total Q, which you will get as 765 kilowatt. Okay, that's what I have in my calculations. You may get a little bit here and there, but hopefully you will get something similar. Okay, Q, then I have calculated Q. Done. Can I find U? What would be U?
Sir, should we
1 over
neglect the
HH.
thermal resistance due to the solid in between?
Yes, exactly. Yes. Okay. So this is what we can do. So here what you have to write is assuming or neglecting the thermal resistance due to the wall, which is not bad. Remember one of the problems I gave you in the last class test? That's what you saw, right? This was pretty much a heat exchanger problem. And typically the walls are made of copper or aluminum, some good conductor of heat, as a result of which, why video is off, is it? Some good conductor of heat, and as a result of which this contribution of the second term is typically negligible. This one. If you do this, if you neglect that, sorry, 1 over U, right? So if you do that, you will see that 1 over U would be 1 over 60 plus 1 over 30, right? So 1 over 60 plus 1 over 30 is actually 3 over 60. So U will be 20 watts per meter squared Kelvin. Okay. So therefore, I have also found U. Remember, this is what I have to find. Acha, baki raha delta Tm. So number 3, how will you do that? Do we know everything for delta Tm? What is delta Tm? Delta T1 minus delta T2. In this case, both will, 1 is inlet, 2 is exit, divided by log delta T1. minus log delta T2. Do I know everything? What is delta T1? THI minus TCI. Yes, I know this. Delta T2, THE minus TCE. I don't know this. Correct? So what will I do? For here, I will say that Q is also equals to m dot C CPC TCE minus TCI. I know everything because Q I just calculated it to be how much? 765 kilowatts. Okay. So this is 765 kilowatts. M dot is 5 kg per second. This also I know 1020 joules per kg Kelvin. TCE definitely I don't know. But TCI I know 90 degrees. See? Okay. So from here you will get TCE and you will get it to be around 240 degrees C. Okay. So if you now put it here, plug it back here, you will get delta Tm, which is the LMTD, would be something like, as per my calculations, would come out to be 228 degrees C. Okay. So put back values of U, delta Tm, and Q. Get A. And A, as per my calculations, is 167.7 meters squared. Okay. Any questions? This is a straightforward problem. Again, just those three equations: Q equals to UA delta Tm, Q equals to MH MCP delta T for both of these fluids, and yeah, that's it. Okay, so very straightforward, but you have to think systematically. This was for parallel flow. Now, I can now do a part B of this question and say, what happens if the heat exchanger is counter flow? The heat exchanger is counter flow. What will happen?
Delta Tm will be the same as delta Ti and delta Te.
Not delta Ti.
T0, tell 0 and TL.
Yes. So you probably know exactly. Wonderful, wonderful. That's what I was trying to see if somebody catches that. This is a, see, normally I think by just by regular inertia of motion, we would say, oh, that's okay. I know what is delta Ti, what is Te. So therefore I can find out what is delta Tm. Okay. But please notice that this is a special case. Where m dot h Cph equals to m dot c Cpc, right? Therefore, delta T remains constant and is equal to THE minus TCI, that is 260 degrees. Q remains the same as before. Okay. Therefore, delta Tm equal to 260 degrees, which implies A is equal to 147.1 meters squared. Okay, this is what you should get, at least something close to this. But look at the thing. However, another thing to notice is the area for counter flow is lower than that of parallel flow, and that is expected. Okay. Any cross flow heat exchanger with the same set of temperatures will require an area which would lie between these two extremes. Okay. This is a statement I'm making without proof. But any cross flow heat exchanger is going to, with the same set of temperatures, is going to have an area lying between these two extremes. Okay, excellent, excellent. I'm really happy that you noticed the fact that this is the special case. Problem 2. So this is another problem similar. (1,000 kg per hour of water at 50 degrees C enters a single pass cross flow heat exchanger and leaves at 40 degrees C. The heat is transferred to cooling water entering at 35 degrees C and leaving or exiting at 40 degrees C. So as you can see, the exit temperature of the hot and cold fluids are the same. If it were a parallel flow heat exchanger, right at the end there would be no heat transfer. But because it's cross flow, it doesn't matter. It can be different. Okay. The question is, calculate the area of the heat exchanger if the fluids are unmixed on both sides and U equals to 1000 watt per meter squared Kelvin and Cp of water is 4.2 kilojoules per kg Kelvin. This you know very well. Okay, how will you do it? So let's first visualize. This is try to do this and try to draw a sketch. Okay. So this is my heat exchanger, and what I don't know. The cold fluid enters at 35 degrees C and leaves at 40 degrees C. Okay. And I think the mass flow rate is also given, right? How much was that? 1000 kg per hour. Hot water. The other things that are given to me is m dot h equal to 1000 kg per hour. U again 1000 watt per meter squared Kelvin. And Cp of both hot and cold 4.2 kilojoules per kg Kelvin. So this is also a very standard problem. The process, I'm not going to write everything here. Process is first calculate Q, and that you can do from m dot h Cph Thi minus Dhe. I have everything. Okay. This, as per my calculations, comes to approximately 11.6 kilowatt. 11,594.4 watts, 11.6 kilowatts. Now this Q is also equals to UA delta T mean, and what is that? That is equals to UA F delta T mean of counterflow Okay. Now this delta Tm of counterflow can be found out. Okay. So at the entry, counterflow is what? 50 minus 40. And then on the other hand, this entry minus exit. Okay, so that is 5. So that would be 10 minus 5 divided by log of 10 by 5. And this comes to 7.2 degrees C. Okay. So the next thing is F. Now to find F, what do I have to do? Since these are both unmixed, it doesn't matter. So I would say let T1 is TH, T2 is TC. Sorry, 3 only. Okay. So what is my capital R? Capital R is therefore THI minus THE divided by TCE minus TCI. THI minus TE is 10 degrees, TCE minus TCI is 5 degrees, therefore R is 2. And what is P? It doesn't matter as long as I have taken 1 as hot and 2 as cold. That should be TCE minus TCI divided by THI minus TCI. What is TC minus TCI is 5, and THI was 40, TCI was THI was 50, TCI was 35. So 5 by 15, and that is equal to 0.33. Okay, so now I should have HX charts. Okay, so this is both unmixed. So this is my what is conversion factor is around point, a little higher than 0.9. Okay, so from the chart I can write F is around 0.91 from F chart. Okay, so now go back and write, therefore area A equal to Q divided by U A F delta Tm of counter flow. Finally, you will get it to be as 1.77 meters squared. Okay, so this was another standard problem where you have to, again, the interplay of these three equations, UA delta Tm, NCP delta T of both fluids. Okay, and you can find out what is the size of this, size as in what is the surface area across which heat transfer can take place. Okay, when we say sizing of the heat exchanger, this is what we mean. It may not finally mean the compact, how compact the heat exchanger is. Of course, it's a it's a measure of how compact it is. But even for this 1.77 meters squared, if you ask, if you give this problem to 10 different engineers, heat exchanger designers, and tell them that this is the configuration. Can you give me a cross flow heat exchanger where the area is effective area of heat exchange is 1.77 meters squared? They can come up with, I don't know, 50 to 100 different designs. Okay. All right. So 10:50 now. We've taken a little more than half an hour. That's fine. And that now takes us to the. Now there are several such problems in the problem sheet which you can please try those. Okay. But however, what I will do now is I will teach you another method which is probably much more used now. I mean, LMTD method is also equally popular. Don't take it otherwise. Don't think that what I'm going to teach you, the epsilon NTU, is an improvement or a more advanced method or so. Please use LMTD wherever possible. Now, this epsilon NTU, it is also called the effectiveness NTU method. Okay. Now, why do we need this? So let me try to give you the context as to why or when this is going to be useful. Okay. So I would say generally we encounter two types of problems. What are those? Type 1. You are given, let us say, the two fluids. What does that mean? It means your m dot h THI, THE, and M dot C, TCI, TCE. Okay. You may not be given all of them, I mean, because maybe one set is given. If THI and THE are given and TCI is given, you can find TCE as well. So any three problems, any three of them is also okay. And you are given U. Okay. And you have to find A, which is what we did. So this type of problem can be solved by LMTD approach. Okay, and we have solved two of them. Now, let me find the second one. Here, what you are given is what those two fluids are. So basically CP, properties of the two fluids. Okay, you are given area and you are given M dot H, TH, I, M dot C, TCI. Let us say to find THE or TCE or both. Whatever. Look at this. Can you solve this using LMTD? How will you solve this problem? This is a given problem, boss. Okay, U is also given, sorry. If you have a heat exchanger and you have and this is practical situation, right? You have at the inlet you have a fluid that needs to be cooled down, so you know the flow rate and temperature. And then to cool it down, you are using a coolant, and at the inlet you control what is the flow rate, what is inlet. But this is a closed bound problem. It's not like this has infinite number of solutions. Right. If the heat exchanger is fixed, so therefore U and A are known. The mass flow rate and inlet temperature fluids are known. Then this is a well-bound problem. It's a well-defined problem. It's not indeterminate. Can you use LMTD?
So we will get a variable inside and outside the logarithm. So then it becomes very complicated on solving it completely.
Yes, you have exactly. You will have to use trial and error. Let us see that exactly what you said. The first one you can use delta T formula. We know that here. See, U, A are known, but for Q we need delta Tm. Okay, for which take calculate delta Tm. Okay. Calculate Q is equal to UA delta Tm. Okay. Q naught, let us say. Use Q naught to calculate TAG. And compare TAG, compare this value to first assumption. Right. And then repeat this, repeat the above till you reach convergence, where your guessed value and calculated value are equal or close enough. So this is complicated, right? I mean, this is not something which is not an ideal process, right? So this is where, you know, what happens is the epsilon NTU method helps eliminate this iterative process. Okay. It is also a non-dimensional form of capturing the performance of a heat exchanger. Okay. The first thing is effectiveness or epsilon. Okay. How do we define it? 1101. Okay, we should be able to cover a bit more. The effectiveness of a heat exchanger is defined as the ratio of the rate of heat transfer in the HX divided by the maximum possible heat transfer. Okay, this is effectiveness, not efficiency, even though, you know, this is what it is called. I mean, I cannot help it. Because remember, I mean, it's a little confusing, because when we talked about fin effectiveness, it is heat transfer that I get with the fin versus over heat transfer I would have got without the fin. And that effectiveness should be greater than 1. This effectiveness, by definition, has to be less than 1, right? Because this is like Q over Q max. Okay. Now, what is Q? Q is m dot h Cph Thi minus The equal to m dot c Cpc Tce minus Tci. equivalent. What is Q max? M dot Cp times the maximum temperature difference that is possible inside the heat exchanger. And what is that? We have discussed before. Thi minus Tci. Okay. Next question is, what is this M dot Cp? Is it the hot fluid or the cold fluid? It is the smaller of the two. Okay. So this is the smaller of the two M dot Cps. Now the thing is, and again I'm making a statement which you can prove actually. If you assume the larger M dot Cp, that is M dot Cp L, what will happen is one of the exit temperatures or entry temperatures will lie outside the THI TCI domain. Okay, this not very, it cannot be readily proved, but it is true. And this is the maximum temperature difference that can exist inside the heat exchanger. And remember, this is for a parallel flow at the inlet of both fluids. Okay, so keep this in mind that for effectiveness, the smaller of the heat capacities have to be multiplied, not the larger. Okay. Therefore, if A,
Excuse me, sir.
yeah,
This is applicable for only parallel flows.
no, it's applicable for everything. Because the denominator is the ideal situation. So if M dot H CPH is less than M dot C CPC, then effectiveness, I will write it in this form. The denominator will therefore be M dot H CPH. So in the numerator also, I will use the hot fluid configuration, hot fluid energy change, into energy change, so that the specific heats get cancelled out, and this becomes, oh, what did I write? Sorry. B, if M dot C CPC is lesser than M dot H CPH, then effectiveness So the denominator remains the same, Thi minus Tci. And the numerator, I will take the cold fluid energy, Q of the cold fluid, would be Tce minus Tci. Okay. And in the special case where m dot h Cph equals to m dot c Cpc, the two definitions or two expressions are equivalent. Okay. And by definition, clear? So this is how we define the first parameter of epsilon NTU, which is called the effectiveness. Okay. All right. So let's break here today, and we will come back on Monday and finish this off. Okay. What we will do is we will start with, we will derive the expression for parallel flow and then give you the expression for counter flow as well. Those are complicated expressions. Thankfully, you don't have to remember. Okay. But while deriving the expression, we will come up with a term which is called the NTU, number of transfer units, which will be defined as UA. Remember UA of UA delta T? That UA divided by the m dot Cp of the smaller m dot Cp. Okay. And once we do that, what you will see is we have charts like these. Okay, these are the F charts. So this is your effectiveness NTU chart, the parallel flow. Okay. So you have NTU in the x-axis, you have epsilon in the y-axis, the effectiveness in the y-axis, and then you have the ratio of the m dot Cp's, which is m dot Cp smaller over larger, which they're talking about C min over C max. We have 1.75, blah blah blah. Okay. So you have these charts for parallel flow, counter flow, cross flow, mixed, a cross flow unmixed, cross flow one mixed, one unmixed, both mixed, shell and tube, blah blah blah. Okay. All right. So similar to the F charts here also, it's complicated. These are a bit complicated, but it's possible to derive. It's possible. I mean, people have already derived it for us. Okay. So that's it for today. Almost 1 hour. So let me stop sharing now. And when we come back on Monday at 10 o'clock, we will, in that lecture, we will wrap up heat exchangers. Okay. So after that, you can enjoy your puja break. I have uploaded the, what is it? I have uploaded the problem sheet of heat exchangers. So please go through that and try to find some time out of your break to solve those. Just 10 problems. And as I said, these are easy ones. Okay. I'm not sure if there are any problems where the heat transfer coefficient have to be determined. If there are, leave it. Okay. We will discuss after we come back. What I'm trying to say is, remember the first problem that we solved, the heat transfer coefficients HH and HC were given to you. But however, when we go through convection, we will learn how to calculate for certain geometries, how to calculate those heat transfer coefficients. Okay, so you may get a heat exchanger problem where they say that there is flow inside a tube and there is flow outside the tube, cross flow outside the tube. Heat exchanger, the heat transfer coefficients will not be given to you. Okay, but we have means to derive what is heat transfer coefficient for internal flow through a tube and also internal cross flow over a cylinder. We will learn all that as part of convection. So I don't remember any such problems, but if there are, please keep them. Otherwise, they're simple problems. Try to solve them, and we will meet. Anyway, we will meet again on Monday, and we will go over this. Okay. When we come back after Durga Puja, we will have our second test and second class test, and the syllabus is going to be radiation and heat exchangers. Okay, as usual, open book, open notes, open everything, open internet. Okay, but no open chat. Okay, all right. Have a good weekend. Have a good rest of the weekend, and see you again on Monday morning. Thank you.